माइक भी चल रहा है ना सर?
Hello, I'm audible. Still not. So welcome to lecture 3. We will conclude our applications of optimization and machine learning, the set of running examples that we have been considering so far. So what we'll be doing today is completing a bunch of examples in the continuous optimization realm and quickly look at some of the discrete optimization applications. Just as a friendly reminder, it's not working. Hello? Hello? Is this okay? Yeah. Just as a friendly reminder, our Teams is active. I think TAs have been conversing with all of you on Teams. So please make sure you're on Teams. Please make sure you're on Moodle. I've been posting all notes, slides, etc. In fact, pre-reading material for each class also on Moodle. Of course, as I said, I'll be having significant variant to the slides based on a lot more LLM development, right? Gen AI developments. So the slides from the last year may serve as a kind of primer, but you should be attending classes. Also, we have for the projects and seminars, we have floated this form. So I hope everyone's able to access this form, and you're supposed to submit this by tomorrow, Tuesday. Oh, it's extended to Friday. I don't know. Okay. So it's extended to Friday, but the form is up there. Okay, so this is where we were. We considered, well, 3.5 applications. We considered supervised learning, principal component analysis, low rank and non-negative matrix factorization. Both of them we considered. And then we got started with clustering. We'll complete contextual bandits, learning from log data with RLHF, and then do a bunch of discrete optimization examples as well. I hope to complete this today and set you rolling for the next set of classes. So recall that on the supervised learning front, we talked about the unsupervised learning, PCA. There's another one, which is the k-means clustering, which I'll talk about today, complete today, rather. We had already started. And then talk about this reinforcement learning from human feedback, agentic systems, right? Right? So clustering, right? So this is an example of unsupervised learning. And as I had alluded to in the last class, it is an example of continuous optimization, but it also has elements of discrete optimization, largely because what you're trying to do in this process of clustering is identify membership, right? So given a set of points, I want to do two things simultaneously, and that's what that was the pictorial depiction from the last class, right? Given the data x1, x2, xm represented in n-dimensional feature space, so these are xi's. What I want to do simultaneously are associate these xi's with potential centroids. Centroids called mu i's, right? Xi's with mu j's. Okay. Oh, I'm using mu I and xj. So there's mu1, mu2, mu3. I need to determine both the mu's. This is mu1, this is mu2, this is some mu I. I need to determine both the mu's and the membership of the xj's to mu i's. This membership is denoted using another another optimization variable, which is the P, the membership to the ith cluster of the jth point, right? Now, when you're considering hard membership, these Pij's are zeros or ones. But you could also have soft membership, where you could have a point belonging to multiple clusters, right? If you have ever come across mixture of Gaussians, so there you're looking basically at membership of points to different Gaussian modes. Okay, so but on the slide, what we have considered is a hard membership. Now, obviously, if I have Pijs in 0 and 1, do I also need the points to belong to exactly one cluster? Can they belong to multiple? Doesn't make sense. Pijs are zeros or ones. You would like to put a constraint, right? The constraint is such that each point j belongs exactly to one I. How do you denote that? Such that summation over I Pij is 1. So you want this additional constraint as well. Okay. So soft K means clustering. I've also shown here. In case you want to keep these Pijs, we also continuous valued. You could associate some distribution, exactly like in the mixture of Gaussians. So I have in my Moodle page, I have actually posted some detailed notes on graphical models where you'll find um, mixture of Gaussians also. Right? So look at the Google Moodle page if you want. But this is the soft version of that. Right? And what you typically do is, okay, if you have come across a very intuitive, iterative way of updating MUIs and PIJs, what would you do? You would say, well, I would make MUIs as a weighted linear combination of the XJs that belong to that cluster, right? So MUI at a time step t is summation over j of Pij t mu j. And based on that, I can update my memberships again. Pij t is proportional to, right? It could be a hard or soft version, but some proportional to the distance between xj and mu I from the previous iteration. You see, this is a very simple iterative approach. But what is the objective function that it is actually, right? This. Sometimes you come up with an algorithm and then try and work out an objective function. Sometimes algorithms are intuitive, right? But what is the objective that it's actually minimizing, right? So the attempt is what we have written on the board, but obviously there are multiple variants. You're basically trying to minimize over all i's and j's, well, rather more specifically all mu i's and pij's. The distance between the ith cluster representative mu I and in some sense whether I should actually consider the contribution of xj to the ith cluster representative, which is measured through a product of Pij and xj. Right? I mean, now you can consider this to be the Euclidean norm square. Again, the multiple choices possible. Is this clear? So this is a continuous relaxation of a totally discrete optimization problem, which I'll talk about later on when we talk about the discrete optimization formulations. Okay. So what are we trying to do? We are trying to find clusters C1, C2, Ck with each cluster consisting of similar instances. So if all the points put together, all the clusters put together are 1 to n, then basically what you are trying to say is if I unite all the, take a union of all the clusters, you should get back V. Right? So what we now, what if we really want this membership that the data is partitioned, right? So this case, the data is actually partitioned, the clusters are disjoint. C1, Cm intersection Cn is empty. Right? So this Pij is then supposed to be constrained to sum to 1 and also to be between 0 and 1. Right? So this will be a discrete plus continuous optimization problem because of the Pij. So this Pij in 0 and 1 and summation Pij equaling 1 across all I for Ej is actually a discrete constraint. This is discrete when you want membership to be discrete. The purely discrete. You could also have a purely discrete optimization problem where the mu i's should also coincide with the data points. See, here the mu i's are allowed to be free. These mu i's are basically, let's say, in Rn. But if you want these mu i's to coincide with the points, as we'll see later on in k-medoid clustering problem, then the problem is totally discrete. Right? Here at least on the mu I front it is continuous. On the Pij's it is discrete. Okay. Okay, so the k-means optimization problem otherwise is written like this. I have kind of taken the liberty of even reducing or getting rid of the mu i's. As you can see, what I've done here is pretended as if the mu I is going to be a mean. Mu I is indeed the mean of all the points that belong to that cluster. Okay, so summation over all points summation over all clusters. Here I is cluster, exactly like on the board. I is cluster. Summation of all points that belong to that cluster, which is the discrete part. This xi, x and ci is a discrete part of x minus the mean of all points that belong to that cluster. So this is the optimization problem. It deceptively looks like a continuous optimization problem, right? You can, if I write this, if I started with this, you would have thought, oh, it's just a totally continuous optimization problem, right? Because the x in Ci innocuously looks like it's easy to find. But the x in Ci is where we have a chicken and egg problem. I'm trying to find the memberships through the Pij's, right? So you can convince yourself that this problem is the same as the problem on the board. So sometimes you'll find, right, objective functions written in such deceitful manner. And you think, oh, this looks like a totally continuous optimization problem, right? So you should not be deceived. Is that clear? Okay. Now is this any questions on this? So it is not a continuous optimization. It's not a completely continuous optimization problem. That's what I'm trying to emphasize. I'm saying that problem on the board is exactly on the slide is exactly the problem on the board. The problem on the board looks very clearly discrete plus continuous optimization problem, and that what you see on the slide is exactly of the same form, just that it can deceive you into believing that it is a continuous optimization problem. So I'm happy you're not deceived, right? It is not. Yeah. Sorry? Mean is in this problem, mean is implied. Okay, that's a good question. Isn't it completely discrete, the other extreme? Because the mean has been implied, right? That's a good point. Yes. We'll come to that, but intuitively, right? If I wanted to cluster, as I said, facilities. I took this example in the last class. If I want to locate warehouses, right? So if I just go by this kind of clustering, so I might land up having one warehouse in the middle of a Godavari river, right? Why? Because it's probably flowing between two different cities. Or in the, I mean, if I look at, warehouses with the Andaman and Nicobar Islands, it may actually end up being in the Bay of Bengal, which doesn't make sense. So you want these to coincide with actual feasible, tangible locations if I want to have a warehouse. So then this kind of mean can be misleading. What we want is a medoid. That's a k-medoid clustering problem. But then that's a purely discrete optimization problem. And in this, the way we have posed it is almost like a discrete optimization problem. Though in reality, this is the problem we are trying to solve. Okay. Of course, there's an assumption here that we are also looking at the L2 norm, right? But if we do away with that assumption, it will actually become a mixed discrete continuous optimization problem. Okay. Now, oh, sorry. So, just a second. I wanted to. Wait a second. Any other questions? If you have, please let me know. As we move to the next topic. Yeah. Okay, so this is an application 6 we're looking at, which has to do with contextual bandits. As an example, but we will begin with RLHF. What is the expansion of RLHF? Reinforcement learning from human feedback. So we will show its motivation, the contextual bandit motivation and connection to large language models. Talk about something called the Simpson's paradox and its relevance to RLHF. And the mathematical optimization objectives, there'll be some discussion on the same. Okay, so, so this is a primer to contextual bandits. So you have a context, right? A context could be, in the example of browsing. So you're a user. You are a user. You have your own profile. You have your demography. You have your own browsing history, and you're firing a search, which is your need. That's also kind of your context. So user along with the search query is a context. In the case of ChatGPT, you're basically posing a query with your own history. That is also your context. The second part is action, right? Action is what the model responds to your context, your query with. So it could be a search results. It could be the case of ChatGPT, a response, right? Sequence of tokens. And the reward is a click or an article. In the case of browsing, in the case of an LLM usage, it could be actually a reward in terms of actually selecting or explicitly mentioning that this response is acceptable. So the objective overall is to select actions. The model should be trained to select actions that maximize reward. Right? So you provide reward, the model should learn. So we'll just keep this simple picture in mind. XT provided by user is going to the model. Now I add a little bit more notation as we progress. And the model basically provides a query. The model is basically going to give a response. And this response is for example, the display of an article. So this is through, say, 80, and the user is going to provide a reward, which is a function of its own input and the model's output. Of course, now this is the case for a single user. The model is going to now take input from multiple such users. So there'll be another user, right? And the model has to work on some objective function to be able to do the best it can to cater to a completely unseen user. So in the context of this RLHF, right? So if you have a query that you pass out to ChatGPT, what is the Virupaksha temple? There could be multiple complex completions, right? So Virupaksha temple is a temple in the historic site of Hampi, which was the capital of Vijayanagar. So Hampi is a correct answer. But since the model might not be specifically trained on Indian, so the model basically generates a token or sequence. Now the feedback could be from human analysts. It's also possible that the feedback is from some automated reward model. So you might actually supply a document to the model, and you want um, the so-called agent to be able to calibrate its output with respect to your document. So it's not necessary that for every output it provides, you explicitly provide a reward. Reward, yes, in some sense is coming from human feedback. It's a human annotator giving the feedback, or some kind of automation set in through a larger mechanism, like in the case of a document itself being provided as an input, right? I think these are possibilities. Okay. So with that, let's consider an interesting scenario here. The network is lost. It's trying to record. I think the ITP network is very flaky. A second, let me just switch to my own. So I'm recording this in Teams. And the Teams ITP network is lost. I need to keep. I think it look like we land up working on hotspots. Yeah. Okay. So what I'll do is I'll actually show you an example of a very much simpler example than what RLHF, you know, I don't, you are about. Consider an app. So let's consider some data. This has to do with interventions for treatment, and there can be applicable to men, and based on the you could measure the number question I have, right? What is interesting is 60% survived, and in treatment A, 95% women survived. So you can see that the number percentage surviving with A is higher than with B, which is 50 and 85 respectively, right? So you would imagine that there is certainly more value in going for treatment A. Why do you think on a combined score, right, the combined score is basically showing that across men and women, treatment B seems to be more effective because treatment B has 80% surviving, whereas treatment A has only 71%. Any guesses? So the one answer seems to be that there are twice as many men. But yet, even if there are twice as many men, why do you think, despite the fact that for men there were more higher surviving for as per A, why do you think on a combined scale B is better? I mean, what you're saying would have made sense if the percentage survival for men was higher using B than using A, right? But here, A is more effective for men, A is more effective for women. But on a combined scale, B seems to be more effective combined across men and women. What's really happening? Okay, so I'll take an example to, I'll run this through again. So this is called the Simpson's paradox. And why do we have the Simpson's paradox?